Good afternoon, everyone. Today we will report about fatigue-resistant lead-free multi-layer ceramic capacitors with ultra-high energy density. So now let's begin to the background of the study. The depletion of fossil fuel reserves and serious concerns over climate change have provoked the development of renewable energy, including tidal, wind, and solar. Electrical energy is currently stored or generated autonomously through a range of devices such as fuel cells and batteries. For energy storage applications, dielectric capacitors have the advantages of discharging speed, superior temperature stability, and are mainly used for pulse power applications such as power distribution, medical transportation devices, and pulse-powered weapons. Dielectric polymers are limited by their low melting temperatures and related degradations. Dielectric ceramics are potentially more temperature stable than dielectric polymers, but have comparatively low recoverable energy density or WREC and energy conversion efficiency or N, due to their low electric field breakdown strength, which is BDS, and high energy loss or W loss. The relationship between BDS and dielectric layer thickness was first published by Gerson and Marshall in 1959. In principle, all solid dielectrics increase their BDS with decreasing layer thickness, culminating in values of greater than 1 MV cm for thin films. In this study, the researchers have demonstrated this effect numerous times, as have several research groups, by fabricating multi-layer capacitors, 10 micrometer dielectric layer thickness. Once good properties, high resistivity, and electrical homogeneity have been demonstrated in bulk ceramics. However, with any given multi-layer, short-circuit pathways can emerge between low resistivity regions as layer thickness decreases, thereby decreasing BDS. The caveat, therefore, which must be applied to the Gerson and Marshall relationship is that BDS will only increase if low resistivity pathways are eliminated. In that, the materials have a high resistivity and are electrically homogeneous. So now let's proceed to theoretical background. To satisfy the requirements of power supply components in portable electronics, electric vehicles, and other high power and energy storage applications, both high rec and N are required. For dielectric capacitors, the total energy density or W, WREC, and N are given by these equations, where P, Pmax, and PR are the polarization, maximum polarization, and remnant polarization, respectively. A high BDS combined with large Pmax and small PR are simultaneously desirable to achieve both high REC and N. Furthermore, the stability and fatigue resistance of materials and devices over a range of temperature and frequency are critical. However, with any given multi-layer, short-circuit pathways can emerge between low resistivity regions as layer thickness decreases, thereby decreasing BDS. The caveat, therefore, which must be applied to the Gerson and Marshall relationship is that BDS will only increase if low resistivity pathways are eliminated. That is, the materials have a high resistivity and are electrically homogeneous. Although high energy storage performance with WREC 10.4 joules per inverse centimeter cube and alpha N 87% has been achieved with La and Sn co-doped lead zirconate at 400 kV inverse centimeter. Lead-free ceramics based on niobium silver trioxide and barium titanite, TiO3, NbO3, and BiFeO3, BaTiO3 have all been studied due to concerns over the toxicity of lead. High WREC has been reported in anti-ferroelectric dope AN with enhanced BDS up to 300 kV inverse centimeter. Oxide additives Al2O3, SiO2, MgO, and BiO3 have all been found to improve WREC and BDS of BT-based ceramics up to 2.9 joules inverse centimeter cube and 300 kilovolts inverse centimeter respectively. In this study, we utilize stoichiometric doping, the nature of which is complex but which has been dealt with by Sinclair and co-workers for several systems, in that BNT-based and BFBT-based materials. Stoichiometric doping has been shown to be effective at reducing conductivity and promoting electrical homogeneity in a wide range of systems.
Materials and equipment, ceramics and MLCC fabrication. BFBT-based ceramic inside the ternary solid solution of 0.7 bismuth ferrite and 0.3 barium titranate were produced utilizing traditional solid-state reaction. Ceramic multilayers were manufactured utilizing an MTI MSK AFA2 tape caster with a single doctor blade on the single-sided silicon-coated mylar film. The PT electrodes were printed onto the tape using the DEK 747 screen printer, followed by tape stacking and hot pressing for 70 degrees Celsius for 10 minutes. Multilayer were sintered at 890 degrees Celsius for 2 hours, with an intermediate binder burnout step 180 degrees Celsius for 4 hours and 300 degrees Celsius for 2 hours. The multilayers were coated with silver terminal electrodes and burned for 2 hours at 850 degrees Celsius. Microstructural characterization. The Archimedes method was used to determine the densities of sintered ceramics, which exceed to 95% of the theoretical density. The phase assemblage structure and microstructure at room temperature were investigated using the X-ray powder diffraction, which is XRD Bruker D2 phaser, and scanning electron microscopy using SEM FEI Inspec F50 with a backscatter detector. For SEM, sintered samples were first ground and then polished to a mirror sheen with wet abrasive paper and diamond paste. Specimens for transmission electron microscopy or TEM were prepared by mechanical grinding, polishing, and iron milling. To minimize surface damage to the specimen, a Gaetan precision ion polishing system was used to perform the ion milling at liquid nitrogen temperature. The JL F200 microscope was utilized for high-resolution transmission electron microscopy and scanning electron microscopy imaging as well as energy dispersive X-ray spectroscopy research. Electric characterization. For electrical measurements, silver was sputtered onto the top and bottom surface of ceramic pellets. The ferroelectric polarization's electric field was measured from room temperature to 225 degrees Celsius using a 1 Hz triangle signal with an AIX ACCT TF 2000E system. Using a LCR meter, the dielectric characteristics were investigated as the function of temperature from room temperature to 600 degrees Celsius at 1, 10, 100, and 250 kHz. Using an Agilent E4980A impedance AC analyzer, the impedance data were collected at 250 degrees Celsius intervals from room temperature to 400 degrees Celsius. The impedance measurements were normalized by the geometric factor and then evaluated with Z-View software. In prior paper, it is described in detail how resistance and capacitance value were derived for the various electroactive regions using Z and M spectroscopic plots.
So the resulting discussion for the high energy density dielectric ceramics using the XRD, the crystal structure of crushed BF, BT, XBN in ceramics where X is greater than 0 and less than 0.15 determined was that, as can be seen in figure 8, the temperature dependent permittivity, and the electric loss data at 100 kHz for BFBT XBL and ceramics are present in figure 8b, and the composition with X which is less than or equal to 0.02 can be seen in figure 8c were not regarded suitable for the energy storage application due to their low BDS, about 120 kilovolts per centimeter, and substantially energy loss composition with where X is greater or equal to 0.05 and less than 0.15 with a strong core shell contrast of a higher potential energy storage and are being investigated further. The undoped BFBT has a biggest grain size about 8 micron. The grain size decreases significantly for BL and dope composition, which can be seen in figure S6 and S7 in electronic supplementary information, accompanied by the formation of core shell microstructure with BIFE bright, which is bright, and BA rich is dark, and BI rich bright GB phase. This can be seen in figure 8D and table S2. The electronic supplementary information, the BI rich bright green boundary phase correspond to impurity peaks in the XRD pattern. In figure 8E and figure S9 in the electronic supplementary information show the unipolar of PE loops of BF, BT, XBLN, where X is greater or equal to 0.05 and less than or equal to 0.15 under Emax, with maximum polarization and changing polarization and Emax values presented in figure S10 with the electronic supplementary information. The maximum polarization and the change in polarization rise linearly with the increasing electric field, with a slight improvement in PR in figure S10, as can be seen in figure S10. The change in polarization and the Emax rise at first, then fall after reaching the maximum values of 32.5 UC per centimeter squared for the X, which is equal to 0.10, and the Emax about 260 kilovolts per centimeter for X, which is 0.13 respectively. Equation 1 and 3 are used to calculate the total energy, the recoverable energy density, and the energy conversion efficiency at various electric fields as shown in the figure S11 in the electronic supplementary information. In figure 8 shows the maximum total energy about 4.74 joules per centimeter cube, and the recoverable energy density, which is about 3.64 joules per centimeter cube, are obtained for the X that equals to 0.13 ceramics at Emax, where the highest energy conversion efficiency, which is 80%, is obtained for the 0.15 X ceramics. So in figure 9 shows the combined Z and M spectroscopy plot at 250 degrees Celsius for X, which in the A is 0.00 and B is 0.13, temperature dependent M spectroscopic plot for X 00 and for the XD, which is 0.13. The electrical microstructure of BT, XBN are investigated by IS as a function of temperature and frequency. The spectroscopic plot of Z and M at 250 degrees Celsius for BT, XBLN with X equals to 0.00 and X is 0.13 as shown in figure 3 for undoped BT, two electrical components are observed in the N spectrum with a capacitance of 6.83 times 10 to the power of 10 and 1.24 times 10 to the power of 9 F per centimeter at 80 Hz and 10 Hz, as can be seen in Figure 9a respectively. Only a single peak is observed in the spectroscopic plot of C and M at 250 degrees Celsius for x equals to 0.13, can be seen in Figure 9b, correspond to a single bulk with capacitance 1.68 times 10 to the power of 10 F per centimeter for the M peak and resistivity of 0.06 ohms per centimeter from the Z peak. It is noteworthy that M peak height is largely invariant in the temperature range from 250 to 400 degrees Celsius, as can be seen in 9D, which is consistent with the flat E to T response observed from fixed frequency dielectric measurement. While in Figure 8b, temperature-dependent spectroscopic plot of M for x which is equal to 0.0 and x which is equal to 0.13 are displayed in Figure 9c and D.
Now for the MLCCs or the multi-layer ceramic capacitors, Figure 10a shows the BSA cross-section micrographs of BF, BT, 13 BLN multi-layers MLCCs, and Figure 10b shows the EDX mapping of each elemental metal distribution. Ceramic capacitors of BF, BT, 0.13 BLN were fabricated with dielectric layers with active electrode area of 5 mm squared to increase the BDS and energy storage properties as shown in Figure 10a and b for this study. Figure 11a shows a TEM image obtained from the interface between the BF, BT, 13 BLN ceramic and PT electrode or platinum electrode. According to the selected area electron diffraction or the SAED patterns in Figure 11, B and C, the ceramic grains are perovskite structured. According to the EDS elemental maps presented in Figure 12D, the amorphous layer is rich in barium and titanium and iron, but deficient in bismuth. Bismuth, however, is present at the surface of the platinum. These similar amorphous layers have been reported in BT-based MLCCs, and their formation can be attributed to binder burnout during the sintering process. Bismuth is reduced at the platinum dielectric interface by residual carbon from the binder. The reduction of bismuth is enhanced by the formation of an alloy with the platinum, driven by the increase in entropy through mixing. The unipolar PE loops and energy storage properties of BF, BT, 13 BLN multilayers are shown in Figure 12a to b. Pmax of 52 microcoulombs per centimeter squared and PR of 4 microcoulombs per centimeter squared are obtained for multilayers at 953 kilovolts per centimeter. The energy storage properties of multilayers are significantly enhanced with respect to monolithic ceramics, yielding a record high of 13.8 joules per cubic centimeter with efficiency of 81% at 953 kilovolts per centimeter, which is the highest value to date for lead or lead-free ceramics and multilayers as shown in Figure 12C to D, fabricated using a scalable powder-based technology. The unipolar PE loops and energy storage properties are shown in Figure 13. Recoverable density is temperature stable from 25 to 100 degrees Celsius, with little variation as a function of frequency from 0.01 to 100 Hz. and cyclic polling up to 10 raised to 4 or 10,000 times. The recoverable density value of the multilayers exhibits negligible degradation after 10,000 cycles of the unipolar PE loops, possibly due to the absence of significant strain at 400 kV per centimeter. The low strain prevents large cyclic changes in dimensions and eventual micro-cracking. Temperature stability is still limited mainly by the conductivity mechanisms, which become active under high electric fields. Nonetheless, in comparison to the polymer-based capacitors with similar energy densities, the materials show a promises for high temperature applications. BT, BF, 13BLN multilayers are rare earth-free with low sintering temperature of 890 degrees Celsius, providing an opportunity for sustainable manufacturing and indicating potential compatibility with silver-palladium internal electrodes. Multilayers with X equal to 0.13 therefore have the potential to replace the lead-based system for pulsed power applications.
In conclusion, novel BIFEO3, BATIO3, BILI, NBO3, BFBT, XBLN ceramics, and multilayers are effectively synthesized using solid-state reaction and tape casting. WREC 13.8 joules centimeter cube was measured at 953 kV cm for multilayers with 8 meters thick dielectric layers. Under an electric field of 400 kV cm, multilayers are temperature stable 10% from the room temperature to 100 degrees Celsius, frequency dependent 5% from 0.01 to 100 Hz, and fatigue resistant 5% up to 104 cycles of the unipolar PE loops. Additionally, BTBF13BLN multilayers are rare earth-free and have a low centering temperature at 890 degrees Celsius, making them ideal lead-free alternatives for energy storage application.
The research demonstrated the significance of electrical homogeneity for optimizing BDS and energy storage in high energy density materials. The performance of lead-free BF-BT XBLN capacitors is demonstrated. This yields a record recovered energy density or WREC of 13.8 joules centimeter cube and an efficiency of 81% for bulk ceramics and multilayers. Temperature stable up to 100 degrees Celsius, frequency independent between 10 to 102 Hz, and low strain characterize multilayers. These characteristics may be advantageous in pulse of power systems. In methodology, it would be better if they used simpler terms in describing their samples. It would be also better if they showed figures to have a very detailed methodology. In addition, the real experiment might have been better documented with images of the appearance of the sample and the actual settings for characterization techniques used in the study. For MLCC multilayers, were sintered at 890 degrees Celsius for 2 hours with an intermediate binder burnout step. The densities of sintered ceramics were successfully obtained by the Archimedes method and achieved less than 95% of the theoretical density. The researchers assume the numerous factors contribute to the excellent properties of these materials. The high value of WREC is a direct result of being able to apply a significant electric field without causing the breakdown of a material whose crystal chemistry is defined to accommodate highly polarizable ions inside a matrix of different sized AbO3 perovskite unit cells. In the results, there are many factors which influence the excellent properties of materials. The high value of WREC is a direct consequence of being able to apply a large electric field without breakdown into a material whose crystal chemistry is designed to house highly polarizable ions within a matrix of dissimilar sized AbO3 perovskite unit cells. The study was cited properly The ideas and principles were supported by all of the reference studies. Numbering format citation was used in citing ideas, which widened the reader's understanding about the topic. And also, the authors declare no competing financial interest.